Hey everyone, and welcome. What if I told you that there's a secret force that explains pretty much everything, from why your salt is, well, salty, to why the air we breathe doesn't just wander off into space? Well, that force is chemical bonding, and in this explainer, we are going to break it all down. Let's get right into it.
Really think about it. You've got atoms like helium or neon just floating around by themselves, totally happy. But then you have others like sodium and chlorine that are super reactive. They're always looking to pair up. It's kind of like a big party in the periodic table, right? You've got your introverts, your extroverts. But why? What makes them act this way?
The answer to that question, the big secret, boils down to just one powerful word: stability. You see, every single atom has one ultimate goal in life: to become stable. Just like you and me, they're on this constant quest to reach a state where they have the least amount of energy and the most stability. And the way they do that is by forming these atomic friendships, which we call chemical bonds. So, to make sure we absolutely nail this topic, here's our roadmap. First, we'll tackle the why. Then, we'll explore the three main types of bonds. That's ionic, covalent, and coordinate. And finally, we'll have a little fun and put ionic and covalent head-to-head in an ultimate showdown. Okay, sounds good? Let's dive in.
Okay, so before we get into the nuts and bolts of how bonds are made, we absolutely have to understand why they're made. Trust me, if you get this part, the rest of the chapter is going to be a total breeze. It all comes back to that big S word: stability. So who are the role models in this atomic world? Who has already achieved peak stability? Well, it's these guys, the noble gases. Think of them as the cool kids of the periodic table. They've got a perfect set of 8 electrons in their outermost shell. That's the magic number, the state of perfect balance we call a stable octet. Their shells are full, which makes them perfectly content, totally unreactive. Stable. They're the ones every other atom is trying to copy.
And that brings us to the official definition. So a chemical bond is really just the glue, that force of attraction that holds atoms together. It's like the friendship agreement that lets them finally get that stable, noble gas configuration they've been dreaming of. This force is what turns all those individual, unstable atoms into the stable molecules and compounds that make up our world.
So how do atoms actually pull this off? Well, they've got 3 main plays in their playbook. First, one atom can completely transfer electrons to another. That gives us an ionic bond. Or they can agree to share electrons. That's a covalent bond. And then there's a special case, where one atom donates a whole pair of electrons to be shared. We call that a coordinate bond. We're going to break down each of these one by one.
All right, first up is our first type of atomic friendship, the electrovalent bond, but you'll almost always hear called the ionic bond, and I like to call this one the giver and taker relationship, because it's all about one atom completely giving away an electron and another one taking it. Now, this whole giver-taker thing doesn't just happen with any 2 atoms. For the deal to work, 3 conditions have to be met. First, the giver has to be willing to let go of its electron easily. In chemistry speak, we say it has a low ionization potential. Second, the taker has to really want that electron. We call that having a high electron affinity. And third, there's got to be a huge difference in how much they each want electrons. One has to be a giver and the other has to be a taker. This is what we mean by a large electronegativity difference.
Now here's where it gets interesting. When that transfer happens, the atoms aren't neutral anymore. See, an atom starts with an equal number of positive protons and negative electrons. But when it gives away a negative electron, it suddenly has more protons, so it becomes a positive ion, called a cation. And the atom that takes the electron now has more electrons and protons, so it becomes a negative ion, an anion. These new charged particles are what we call ions.
Okay, enough theory. Let's see how this actually plays out with maybe the most famous atomic love story in all of chemistry: the formation of everyday table salt, sodium chloride. First, let's meet sodium. Its electron setup is 2-8-1. See that one lonely electron in its outer shell? That's the source of all its problems. It makes sodium unstable and super reactive. All sodium wants in life is to just get rid of that one electron so it can have a stable outer shell just like the noble gas neon. It's the perfect generous giver. And then along comes chlorine. Its configuration is 2-8-7. Oh, it's so close. It has 7 electrons on the outside and it just needs one more, just one, to complete its octet and become stable like argon. It is a very eager taker. I think you can see where this is headed, right? And it's a perfect match. That single outer electron from sodium literally jumps over to the chlorine atom.
So now, sodium has lost an electron, making it a positive sodium ion, Na+, and chlorine has gained an electron, making it a negative chloride ion, Cl-. And what happens when you put a positive and a negative right next to each other? That's right, they attract. That powerful magnetic-like pull, the electrostatic force of attraction, that is the ionic bond.
Now this is what's so cool. An atom and its ion are like two totally different beings. The sodium atom, it's a silvery white metal that's so reactive it'll explode in water. But the sodium ion, it's completely colorless and totally inactive. The atom is unstable and neutral, the ion is stable and charged. This amazing transformation is the entire point of chemical bonding, to get to that stable, happy state.
And this give-and-take dance isn't a one-time thing. It's a pattern all over the periodic table. Take an atom like magnesium. It has 2 electrons it wants to get rid of. So what does it do? It finds 2 chlorine atoms to make a deal with. Or look at calcium. It also has 2 to give, and it finds a perfect match in oxygen, which needs exactly 2. It's all just a bit of atomic math to make sure everyone gets a full, stable outer shell.
Okay, so we've seen the world of giving and taking. But what happens when you get 2 atoms that both want to be takers? Neither one is going to give up an electron. Well, let's move on to our next type of friendship, the covalent bond. This is where atoms figure out that if you can't take, you share. Yep, for these bonds, sharing is caring.
A covalent bond is all about mutual sharing. It usually happens between 2 nonmetals. So instead of one atom losing an electron and the other gaining it, they each put an electron into the middle to form a shared pair. That shared pair then kind of belongs to both of them. This way, both atoms get to count those shared electrons in their outer shell and both achieve stability. It's a win-win.
Now, this sharing deal can come in a few different flavors. Atoms can share 1 pair of electrons, which we call a single bond. If that's not enough to make them stable, they can share 2 pairs, forming a double bond. And in some cases, for ultimate stability, they can even share 3 pairs of electrons, forming a really, really strong triple bond. It's like going from a simple handshake to a super strong pact.
Let's look at the easiest example there is, hydrogen. A hydrogen atom just has 1 electron. To get stable, like its closest noble gas, helium, it needs 1 more. So when 2 hydrogen atoms get close, each one contributes its single electron. They form 1 shared pair, creating a single covalent bond. And now, both atoms get to count 2 electrons in their outer shell, and they're both stable and happy. Simple.
That's pretty straightforward for hydrogen, right? But what about atoms that are missing more than just 1 electron? What if an atom needs 2 or maybe even 3 more electrons to be stable? Well, that's when they have to level up their sharing game.
And this is where sharing gets really impressive. Take nitrogen. A single nitrogen atom has 5 electrons on the outside, so it needs 3 more to get to that stable octet. So when 2 nitrogen atoms come together, each one puts 3 electrons into the middle. They end up sharing a grand total of 3 pairs of electrons, forming an incredibly strong triple covalent bond. This makes the nitrogen molecule, N2, so stable that it makes up about 78% of the air we breathe.
Okay, one last important point about sharing. Sometimes the sharing is perfectly equal, a perfect 50-50 split. This happens when 2 identical atoms bond, like in H2 or O2. We call this a nonpolar covalent bond. But other times, one of the atoms is a little bit greedier. It pulls that shared pair of electrons just a little closer to itself. This unequal sharing creates a slight negative charge on the greedy atom and a slight positive charge on the other one. That's what we call a polar covalent bond, and you see it in really important molecules like water.
All right, team, we have met our 2 main players, the ionic bond, the giver and taker, and the covalent bond, the one based on sharing. So now, it's time for the main event. Let's put them in the ring, head-to-head for the ultimate showdown and see just how different their properties are.
This table tells the whole story. So, in one corner we have ionic compounds. Because they're built from those strong positive and negative charges locking together, they form these hard, solid crystals. It takes a huge amount of energy to break those bonds, which means they have super high melting and boiling points. Now, in the other corner, you have covalent compounds. They're made of neutral molecules with much weaker forces between them. That's why they're often gases, liquids, or soft solids that melt and boil much more easily.
And here is a huge difference: conducting electricity. Check out this experiment. When you dissolve an ionic compound, like salt, in water, it breaks apart into free-moving ions.
Those charged particles can carry an electric current, so the solution conducts electricity and the light bulb glows. But covalent compounds, they don't have ions. Dissolve sugar in water, you just get neutral sugar molecules floating around. No free charges, no current, no light. This is a really key, practical way to tell them apart.
So we've covered giving, taking, and mutual sharing. But wait, there's one last, very special type of bond we need to cover. It's a kind of covalent bond, but it has a really cool twist. Welcome to the world of the coordinate or dative bond, a relationship built entirely on one generous donor.
For this special bond to happen, two things have to be true. First, you need an atom that's already stable, but it has what we call a lone pair, a pair of outer electrons that isn't already busy in another bond. This is our generous donor. Second, you need another atom or ion that is really short on electrons and needs a pair to become stable. This is our friend in need.
The classic example that you'll always see is the ammonium ion. So look at this ammonia molecule, NH3. The nitrogen in the middle is happy. Its octet is complete. But you see that pair of dots sitting on top of the nitrogen? That's its lone pair. Now along comes a poor little hydrogen ion, H+. It's just a proton. It has 0 electrons. So the generous nitrogen atom donates its entire lone pair to form a brand new bond with that hydrogen ion. This bond where both electrons came from just one of the atoms, that's the coordinate bond.
And we see the exact same thing happen in water. A water molecule, H2O, actually has 2 lone pairs on its central oxygen atom. So when it bumps into a hydrogen ion, that oxygen generously donates one of its lone pairs to form a coordinate bond, creating the hydronium ion, H3O+. This is another super important example you absolutely need to know.
Whew, okay, that was a lot. So let's do a super quick recap of the 3 atomic friendships we learned about today. The ionic bond is all about a complete transfer of electrons, our giver and taker. The covalent bond is about mutual sharing, where sharing is caring. And the coordinate bond is that special case, a one-way donation of a shared pair, our generous donor.
But in the end, it doesn't matter if it's ionic, covalent, or coordinate, it all comes back to this one fundamental idea stated perfectly right here. The whole reason any of this happens, the entire cause of chemical combination, is just the simple tendency of atoms to get that stable, noble gas configuration. That's the endgame. That's what it's all about.
And to leave you with a little something to chew on, here's a challenge question for you. There's a compound mentioned in your book that has all 3 types of bonds we just talked about, ionic, covalent, and coordinate, all inside one single structure. Go back through the chapter, see if you can find it, and let me know what you find in the comments below. I'll be looking forward to seeing your answers.
You guys did a fantastic job today. From givers and takers to sharers and generous donors, you now have the whole story of how atoms form bonds. Just keep going over these core ideas, and I promise you're going to master this chapter in no time. Keep up the awesome work, and I will see you in the next explainer.